Now, yesterday we heard a lot about Moore's Law. The power of this technology gives us unbelievable access in our hardware devices to be able to do more applications. We have GPUs, FPGAs, multi-core and many-core applications. But of course, the challenge with Moore's Law is on the software side. We have to ensure the tools keep up so that the developer efficiency stays on par. Now, this situation is what causes the software industry to keep pushing the limits of abstraction. We have to continue to give you more productive tools so you can address these extremely complex applications. Now, this is really a view of the processor space. If we look over at the digital design space, they don't have access to as much abstraction, as much productive tools. In fact, about 15 years ago, a concept called high-level synthesis was in the digital design space. And this was really a testament to the need for more abstraction. Engineers were trying to access and use FPGAs for more and more applications, but they needed the right tools to do so. Now, many of you know, almost 10 years ago, we introduced the LabVIEW FPGA module, which is absolutely a step function in productivity and a type of high-level synthesis. But of course, we didn't want to stop there. We continued to look at technologies. We continued to work with technology partners like Xilinx to look at the latest technologies out there. What are the new techniques in high-level synthesis? Because we want to expand and grow the possibilities for what LabVIEW FPGA can do to all the system designers in the space. So to share with you now how we're incorporating some of the latest HLS or high-level synthesis technologies into our own tools, please join me in welcoming from the NI team, Alan Moriat, Dr. Doug Kim, and Tiang Li. Welcome, guys.
Hey, Shelly.
Hey, Alan.
How are you today?
I'm doing great. It's good to see you. Now, Alan, I know that you're using some of these new HLS technologies in some of your own research. Could you share with us?
Sure. I've been looking for ways to use FPGA to push the boundaries of what our platforms can do, especially for image processing. So as you probably know, FPGAs are great to build dedicated hardware that can accelerate all sort of algorithm. So as an example, let me invite you to the world of fractals, like the Manbrod set you see behind me.
Well, Alan, I love fractals. I'm glad you're bringing fractals to the stage today.
That's cool, but you know, Manbrod is just not a simple, pretty picture. It's also very useful to benchmark, for example, accuracy and speed of fixed point calculation. So the core algorithm is very simple. It's a simple formula running a number of times in an iteration loop. But that core has to run on every single pixel in the image. And that's where, obviously, the FPGA nature of parallelization can help us. So I wanted to compute 64 pixels at the same time. So I tried to drop 64 instances of my VI on the main diagram, but it became pretty quickly unreadable and very difficult to maintain and modify.
It looks unreadable to us, too.
Yeah, and even when I did that, I really never achieved the real-time rendering performance I was looking for. But guess what? That's when I heard that Tianming and his team were working on a new add-on for LabVIEW FPGA. Isn't that right, Tianming?
Yes, Alan. So we've been busy working on a new tool that increases LabVIEW FPGA design efficiency. Today, I'm very pleased to announce the first official release of LabVIEW FPGA IP Builder.
That is very exciting. Thank you, Tianming. Congratulations to you and your team in Shanghai.
Okay, so with this tool, Alan did not need to manually hand optimize his code. You can recognize his 1 pixel processing VI here. We simply wrap it within a for loop with fixed 64 iterations. And then we use a separate project item to specify the kind of optimization or performance requirement. All these are going through a dialog-based interface. So on this dialog, we can see our code. I can find my for loop and optimize the for loop by specifying an on-row factor of 64. So this will direct the LabVIEW FPGA IP Builder to give us 64 parallel pixel processing cores.
So with the new LabVIEW FPGA IP Builder, you can select different parts of your block diagram and then specify your directives or optimizations, whether you want to increase your throughput or your silicon size and space. Is that right?
Yeah, that's right, Shelly. So what's more, the tool can provide an estimate of performance and resource usage within minutes, that allowing Alan to iterate among many different optimization ideas without a full FPGA compilation.
I know anyone that's programmed FPGAs will appreciate that feature. You can iterate on your algorithm without having to wait for all of those compiles. So with all these new tools and technologies, Alon, what did you actually build?
Well, I happened to be hit by the transceiver fever, so nothing less than the VST.
We heard a bit about the VST.
From yesterday.
Our reveal was also.
Vertex 6 chip. So as you can see, Tianming is now able to navigate and zoom in real time through the Manbrod set all the way down to 1 billion times.
How many times, Alon?
1 billion, 1,000 millions actually.
Impressive.
So, but Tianming, hey, why don't you show us some cool locations?
Okay, here you go.
So it's really like flying through the universe between galaxies, going back in time and trying to find the location where it all started. Technology Big Bang. Shelley, do you actually know who those guys are?
Alon, I think that may have been our founders a really, really long time ago.
Oh, uh-oh, I'm in trouble.
See one of them.
Okay, back on us. Seriously, a demo like this would really have been difficult to build without the help of the FPGA IP builder and HLS technology. And of course, not to forget very cool hardware.
Absolutely, very cool application, Alon, and running all of that on the VST. Certainly a non-traditional use of using LabVIEW FPGA in the VST. But whether you're working with fractals or designing the next RF communications design, I think this platform is really useful. Now to tell us a bit, we have our own Dr. Doug Kim. He's an RF communications specialist at National Instruments, and he's been using some of these new technologies with some of our lead users.
That's right, Shelley. We've been working closely with some of our lead users who've recently created a complete end-to-end wireless communication system that's capable of streaming HD video.
HD video, all of our smartphones can already do that. Why is that such a big deal, Dr. Kim?
Now, while these services may not seem so impressive nowadays, I'd like to point out the fact that creating such systems is extremely complex. The OSI system model consists of many different layers, each of which represents a very complex set of specifications, which require the expertise of many domain experts with many different backgrounds. Each layer also consists of many different pieces, oftentimes difficult to integrate well together, and the tools required to create these pieces are not necessarily optimized to interoperate well with each other.
So, Doug, can you explain why each of these layers is actually so complex?
Sure. Let's take a closer look at the receiver's physical layer. Here, functions actually generate and consume data at differing rates. As you can see, the received signal is sampled at 50 megasamples per second and undergoes several rate changes all the way down to 6.144 megasamples per second at the output of the synchronization block.
So I'm guessing with all of that, you still have to deal with the buffering and the handshake of all these signals.
Exactly. And these are the fine details associated with multi-rate DSP that designers have to manage very carefully. It only takes a very small mistake for the whole system to fail.
So this view that we're looking at is a very logical representation of the system, but we know researchers are trying to actually implement these. What software tools are you recommending for people creating these types of systems?
The ideal tool to accomplish this is LabVIEW FPGA DSP design module, which enables users to express their ideas in a more natural representation, one that more closely resembles what you might sketch up on a whiteboard.
Yeah, exactly. I mean, this view closely resembles the diagram we saw before, but I don't see any buffers, I don't see any FIFOs, the wiring looks really simple.
That's right, and it's not all just looks. There's actually a lot going on under the hood. For instance, by specifying the number of sample counts that each block consumes and generates as shown there, along with your desired throughput, as shown here, the tool will actually automatically calculate all the optimal buffer sizes throughout your entire diagram, like that shown there.
So we discussed a little bit with Dr. Clegg earlier about this concept of models of computation. As a DSP designer or an expert in your field, it sounds like this new tool, the DSP design module, is a very natural representation to represent that kind of development. So it sounds like we're also going to announce today a new model of computation that allows you to map your multi-rate DSP algorithms all the way to hardware. Tell us about how the Rutgers University team is using this new model of computation.
They've actually created their own complete end-to-end wireless communication system that streams HD video It also includes an advanced channel decoder that was created using LabVIEW FPGA IP Builder. As you can see, both the transmitter and the receiver consist of multiple layers of the OSI model, where each element within the system was built using LabVIEW. How about we take a look at their system in action?
And to prove that it's not just streaming a video, because that's easy, I'll actually break the signal in real time and see if I cause interference in the video.
So, as we've seen, LabVIEW, along with all its software tools, including DSP design module and LabVIEW FPGA IP Builder, has streamlined the design process in creating a complete end-to-end wireless communication system.
And Dr. Kim, it looks like your lead users actually agree with that statement of the power of all these technologies used for RF communications design. Thank you all for sharing with us this morning.
Thank you.